In this video we're going to start using trigonometric ratios with angles expressed in radians. You should by now know the graphs of the basic trigonometric functions when the angle theta is measured in degrees. So we've got the cosine graph and the sine graph, both of which are oscillations with an amplitude of 1 and a period of 360 degrees. And the tangent graph has a period of 180 degrees and it has vertical asymptotes at 90, 270, 450, 630 and so on when theta is measured in degrees. Now when we move to using radians instead of degrees, then the graphs have exactly the same shape as before, but the theta axis is revised so that 90 degrees becomes pi by 2 radians, 180 degrees becomes pi radians, 270 degrees becomes 3 pi by 2 radians, and 360 degrees becomes 2 pi radians. So the graph of y equals cos theta, where theta is measured in radians, is here. It's again an oscillation, and it's an oscillation with period 2 pi and amplitude 1 unit. Similarly, the graph of sine theta is an oscillation with amplitude 1 and period 2 pi. The graph of y equals tan theta, where theta is in radians, looks exactly like the tan graph before, except that we've changed the theta axis again. So we've got a graph that is repeating every pi, and it has asymptotes at theta equals pi by 2, theta equals 3 pi by 2, theta equals 5 pi by 2, etc. Provided our calculator is switched to radian mode, then calculations involving trigonometry with angles expressed in radians can be performed easily using the same methods as would have been used with degrees. So the important thing is to make sure that we know how to switch our calculator between degree mode and radian mode. If you're using a Casio FX991, also known as a ClassWiz calculator, you'll see that in the top of the screen there's a little D, and the little D there signifies that the calculator is currently in degree mode. If it's a little R, then it shows that it's currently in radian mode, and if it's in G, it's in a mode which measures angles in a way that in Britain we don't use. So for trigonometric calculations involving degrees, you must ensure that that D is on the top line of the screen there, and for calculations involving radians there must be an R at the top of that screen. How do we change it? Well, if we need to change it from degrees to radians, we need to press first of all the Shift button and then the menu setup button, which are highlighted now on the diagram. Having done that, you obtain a screen like this, and if you now press number 2, that will enable you to change the angle unit. The screen revises to give you the possible choices. So if you want to change from degrees to radians, you'll need to press the number 2 again. If on the other hand you want to switch from you're currently in radians and want to switch to degrees, you'll need to press the number 1. So should now be able to use your calculator and switch between degree mode and radian mode confidently. So let's have a look how we might do that. So first of all, find the length PQ in the triangle sketched in the diagram. Well, in this case we've got two sides of the triangle, and we've got the angle between the two sides is given in radians, so we can use the cosine rule to find the size of PQ. So we've got PQ squared is 6.4 squared plus 5.2 squared minus 2 times 6.4 times 5.2 times cos of 0.7. And provided we are in radian mode, that will then give me PQ squared equals 17.092. So PQ is 4.134 centimeters. For our second example, the diagram shows a segment of a circle of radius 8 centimeters. The segment subtends an angle of 1.8 radians at the center of the circle. We've got to calculate the area and length of the perimeter of the shaded segment. So, if we take the sector OAP, then we can use our formula, a half r squared theta, for the area of a sector where the angle theta is expressed in radians, to obtain a half times 8 squared times by 1.8, which gives me 57.6 centimeters squared. If I use the formula for a triangle of a half AB sine C, where little a and little b are two adjoining sides and C is the angle in between the two adjoining sides, then I get the area of triangle OAP is a half times 8 times 8 times sine of 1.8, and that will give me 31.16 centimeters squared. The shaded area is the area of the sector minus the area of the triangle, so that is 26.44 centimeters squared. Now we've also got to find the length of the perimeter of the shaded segment, and the perimeter consists of the arc joining A to P plus the length of the line joining A to P. The arc is easy because if we're using radians, the formula for arc length is simply r times theta, which in this case gives me 8 times 1.8, which is 14.4 centimeters. The length AP can be worked out by marking the point M at the midpoint of AP. Then the triangles OAM and OMP are congruent, and they're each right-angled triangles. So we can say that AM, using right-angled triangle work, is going to be 8 times by the sine of 0.9. The length of the line AP then is twice the length of the line length of AM, so that's 2 times by 8 sine 0.9, which gives me 12.53 centimeters. So the perimeter of the shaded area is 14.4 plus 12.53, which gives me 26.93 centimeters. When we're looking at segments, as we were in that last example, a chord drawn across a circle of radius r splits the circle into two segments. The minor segment, or the smaller segment, together with the major segment, which is the rest of the circle other than the minor segment. The working that we did in the previous example generalizes to give us a formula for the area of the minor segment, which is a half r squared theta. That's the area of the sector minus a half r squared sine theta, which is the area of the triangle. On the other hand, if we're looking for the area of the major segment, perhaps the easiest way of doing that is simply to say that the area of the major segment is the area of the circle minus the area of the minor segment, and use the previous formula to work out the area of the minor segment. And to finish the video, we're going to solve 3 equations involving trigonometric functions defined on domains which are given in terms of pi, which certainly suggests that we are working in radians rather than in degrees. For the first one, we've got cos theta equals 0.8, so it's worth starting straight away with a quick sketch graph of cos theta. We've put in a dotted line at roughly 0.8. We can obtain the first place where cos theta equals 0.8 by using the inverse cosine function, but we must make sure that we are working in radian mode if we wish the answers to be in radians. So cos theta equals 0.8. The inverse cosine function tells me that theta then is 0.6435. So that gives me one solution which I can mark onto my sketch, and I can then use the symmetry of the graph to say that the other solution is going to be 0.6435 before 2 pi. In other words, the other solution is going to be at 2 pi minus 0.6435, which gives me a solution of 5.6397. So the solutions of the equation cos theta equals 0.8 for values of theta between 0 and 2 pi are theta is 0.6435 or 5.6397. Moving on to the second equation, we want to solve the equation sine phi theta equals 0.5 for values of theta between 0 and pi. The first thing I would suggest doing on this is to make a little substitution. Let z equal phi theta, so the equation now becomes sine z equals 0.5 with the smallest possible value for z being 0, that's 5 times 0, but the biggest possible allowed value for z is 5 times pi because z is 5 times theta. So when we make the substitution, we obtain the equation sine z equals 0.5 with z being any value between 0 and 5 pi. Using our calculator and a sketch graph of y equals sine z between 0 and 2 pi will enable us to find two of the roots of the equation sine z equals 0.5. The calculator gives us z as the inverse sine of 0.5, which gives me 1/6 pi. And when we look at the symmetry of the sine graph, we can see that another root will be at pi minus 1/6 pi. In other words, when z equals 5/6 pi. So we've got two roots. We've got 1/6 pi and 5/6 pi. But we know that the sine graph is periodic with period 2 pi. So there will be another root at 1/6 pi plus 2 pi, another root at 5/6 pi plus 2 pi, another root at 1/6 pi plus 2 pi plus 2 pi, in other words 1/6 pi plus 4 pi, another root at 5/6 pi plus 2 pi plus 2 pi, in other words 5/6 pi plus 4 pi. There won't be any more after that because the next one on would be 1/6 pi plus 6 pi, and that is bigger than 5 pi. So is outside the interval in which we're interested. So we've now found that the solution of the equation sine z equals 0.5, where z lies between 0 and 5 pi, is given by z equals pi by 6, 5 pi by 6, 13 pi by 6, 17 pi by 6, 25 pi by 6, and 29 pi by 6. But we must remember at this stage that z is equal to phi theta, which means that theta, what we're really interested in, is equal to 1/5 z. So the solutions of the equation sine phi theta equals 0.5, where theta lies between 0 and pi, are given by theta equals 1/5 of the previous z values that we had. So we've got theta equals pi by 30, pi by 6, 13 pi by 30, 17 pi by 30, 5 pi by 6, and 29 pi by 30. Moving on to the third example, we've got tan of 3 theta plus pi by 4 must equal minus root 3, where the value theta can lie anywhere between 0 and pi. So again, we're going to do a little substitution. We're going to let z equal 3 theta plus pi by 4. The smallest value of theta we're allowed is 0. So the smallest value of z that we're interested in is going to be 3 times 0 plus pi by 4. In other words, pi by 4. The largest value of theta we're interested in is pi. So the largest value of z that we're interested in is 3 pi plus pi by 4, which is 13 pi by 4. So our equation becomes tan z equals minus root 3, where z lies between pi by 4 and 13 pi by 4. Our calculator, together with our knowledge of the shape of the tan graph, will enable us to find the roots of the equation. So the tan graph will look like this. Using the inverse tan on our calculator gives me a possible root as being z equals tan to the minus 1 of minus root 3, which gives me minus pi by 3. Unfortunately, minus pi by 3 is not a root of the equation that we're looking for because it doesn't lie between pi by 4 and 13 pi by 4. However, the tan graph repeats every pi. So there is a root between pi by 2 and pi, and that root is minus pi by 3 plus pi. Similarly, minus pi by 3 plus 2 pi will be a root, and minus pi by 3 plus 3 pi will be a root. The next one along, though, would be minus pi by 3 plus 4 pi, and that's outside the interval, because minus a third pi plus 4 pi equals 11 pi by 3, and 11 pi by 3 is bigger than 13 pi by 4. So the solution of the equation tan z equals minus root 3, where z lies between pi by 4 and 13 pi by 4, is given by z equals 2/3 pi, 5/3 pi, or 8/3 pi. Now we've got to remember at this stage, though, that z is equal to 3 theta plus pi by 4. In other words, theta is 1/3 of z minus pi by 4, or equivalently, it's equal to 1/3 z, take away pi by 12. So we can now calculate the corresponding values of theta. So we've got the roots of the equation tan 3 theta plus pi by 4 equals minus root 3, which satisfy theta lies between 0 and pi, are 1/3 of 2 pi by 3, take away pi by 12, which gives me 5/36 pi, 1/3 of 5 pi by 3, take away pi by 12, which gives me 17/36 of pi, or 1/3 of 8 pi by 3, take away pi by 12, which gives me 29 pi by 36. And that example concludes our look at using trigonometry where the angles are expressed in terms of radians.